Solving general chemistry problems. Reaction kinetics. There is some considerable value in focusing our attention on some simple rate laws. When alcohol is consumed, it is absorbed into the bloodstream, mainly through the small intestine. The concentration of alcohol in the bloodstream rises quickly. One common measure is blood alcohol content, or BAC. A measure of 0.08 grams of ethanol per 100 milliliters of blood is considered impaired for legal purposes in certain jurisdictions. This amounts to a concentration of about 17.4 millimolar. Once in the bloodstream, alcohol is metabolized by a wide spectrum of enzymes in the liver, turning it into acetaldehyde and then into acetic acid, from which it is finally consumed in the citric acid cycle. Once a person's BAC has peaked, alcohol is removed from the system at a constant rate of about 3.3 millimolar per hour. It does not matter whether they drank a lot or a little, the rate at which it is removed is the same. The reason for this arises from the fact that the amount of enzyme available for metabolism is fixed and limiting. You can add in more alcohol, but the rate does not change. In such processes, the rate law describing these chemical kinetics is simply rate equals K. There is no concentration dependence. The concentration of alcohol is raised to the exponent of 0. The language used to describe such a kinetic process is to say that it is a zero-order process. The label order is used to characterize the exponent involved in the rate law. It is a useful descriptor in simple rate laws. In complex rate expressions, the description may not have much meaning, but we can often use it to describe many kinetic situations. Rate equals K is the rate law for a zero-order kinetic process. A widely used anti-cancer therapy drug is cisplatin. It is a comparatively small molecule with a central platinum atom surrounded by 4 ligand molecules, 2 chloride ions, and 2 ammonia molecules. The cis part of its name arises because the ligands have the same type are next to each other. There's a trans platin molecule as well, but they're opposite to each other, but that molecule, just that simple rearrangement of the order of the ligands, does not have any therapeutic value. When cisplatin is introduced into the body, it's administered intravenously, it is hydrolyzed when exposed to water. One of the chloride ions is replaced by a water molecule, and it is this equated version that is physiologically active. The water ligand is readily replaced by binding with guanine in a strand of DNA. Once bound, the other chloride can be replaced with another guanine, and the two sites then cross-link to each other. This inhibits the DNA replication process, and when the cell is unable to repair the damage, the cell initiates apoptosis and the cell dies. The therapeutic strategy is that this process will have the greatest effect on rapidly dividing cells, which are the cancer cells. Now, a simplified study of the concentration of cisplatin following an injection leads to a graph such as this. If you compare this graph to that for the zero-order process for the metabolism of alcohol, you will notice how this graph has a curve to it. The zero-order graph was straight and went right down to the zero line. By contrast, the conversion of the cisplatin slows down as there is less and less of it available. This particular reaction has a rate law that is proportional to the first power of cisplatin concentration. We would write that the rate equals K times the cisplatin concentration. This is a first-order reaction rate process. Butadiene is an important precursor molecule in the chemical industry. It polymerizes in many different ways to produce synthetic rubber or nylon or a host of other materials. It is a gas at room temperature, and there is a reaction by which it combines with itself to form the dimer in the gas phase. We are able to follow the concentration of the monomer as it converts to the dimer. Now here's a graph of that process. Notice how it drops non-linearly like the first-order process. Let's just compare those two curves. Here I've superimposed the first-order curve on this graph as the gold dotted line. You can see that they do drop off in a different manner. This process decreases more quickly at first, but then decreases more slowly later on. We will shortly look at how we can distinguish these two processes. The bottom line, however, is that this reaction depends upon the square of the concentration of the reactant butadiene. The rate equation takes on this new form, and this is referred to as a second-order reaction. These three reaction processes, zero, first, and second order, are the most fundamental reaction processes with which we will explore kinetic theory. Things can get considerably more complex, but these are nicely able to introduce the fundamental concepts of the theory. In studying the kinetic details of these reactions, we will look at them through the lens of an imaginary reaction. A turns into B. We will start by following the change in concentration of the reactant A. The reaction rate is related to the negative of the rate of the disappearance of A. Each of these three reaction processes can now be written as a differential equation. In the case of the zero-order reaction, the differential equation is written in this fashion. Here is the form taken by the first-order reaction equation. Now I've subscripted the rate constant K to the order of the reaction just to keep them straight. They really are unrelated to each other. Finally, this is how the differential equation for the second-order kinetic process is written. You can see again how the order of the reaction is the exponent to which the reactant concentration is raised in the differential equation. These equations tell us a lot about the kinetics of the processes. A different perspective is obtained if we now solve these differential equations to obtain an expression for the way that the reactant concentration changes with time. Now, these are known as the integrated rate laws. For each reaction order, the time derivative of the concentration equates to a different function of concentration, which defines each differential equation. These differential equations are very easy to solve. We just rewrite the differential expressions while separating the concentration differential on one side and the time differential on the other side. We keep the constant K with the time differential just because it makes more sense in the end. Take the zero-order process. Here's the differential equation. Bring the dt to the other side, bring along the negative sign and the k0, just a convenient way to organize the equation. Now you can integrate both sides. Time is integrated from 0 to time t, and from your calculus course you know that the integral of dx is just x, integrated between the upper and lower limits. So our final equation tells us that the reactant concentration will be a straight line decrease from the initial value of a sub 0 right down to 0. That is exactly what we saw with the metabolism of alcohol in the body. Now compare this with the first order process. In this case, the differential equation is a function of the concentration of A. Now we need to not only bring the dt over to the other side, we also have to divide through the A to the opposite side. The left-hand side is a function of only concentration of A, and the right-hand side is only a function of t plus the constants. For these integrals, we not only have to remember that the integral of dx is x, but also that the integral of 1 over x is ln of x. We again apply the upper and lower limits. Now recall how to combine the logarithms. When two logs are subtracted from each other, it is the same as the logarithm of the ratio of the two terms. We get rid of the logarithm by exponentiating both sides. And this is what we saw with the hydrolysis of cisplatin, an exponential decay of the concentration of the precursor molecule. And now for the second order process. The differential equation has a raised to the power of 2. We again get all the terms involving a on the left-hand side and dt with the rest on the right-hand side. The integral we need to recall this time is that of 1 over x squared, which you should recall is minus 1 over x. The minus sign cancels the minus on the other side, and after applying the upper and lower limits, we have an expression that drops inversely with time. The inverse function and the exponential decay of the first order reaction sort of look similar, but they are different in the details. We saw this when comparing the cisplatin reaction with the dimerization of butadiene. This can be rewritten so that it shows the expression for A directly rather than the reciprocal of A. You should be able to see how to rewrite the first equation as the second one. You should remember and understand these equations. Be sure you can recognize the nature of the graphs that they produce: a linear function, an exponential function, and a reciprocal function. Now here's a question for you. These questions correlate with the graphs that we have seen earlier. Here's a reminder of what they look like. But they are all looking at how the reactants disappear with time. If we were to follow the appearance of a product, what would these curves look like? Now take a few minutes, pause the video, and see if you can envision how they would appear. Then restart the video. Okay, we're back. Here are the product curves. They are increasing functions this time, but still have the general shape of the curve: linear, exponential, or reciprocal. They all go towards a final concentration determined by the amount of reactant at the beginning. Note the difference with the second order curve. Because the reaction is one of dimer formation, the product concentration is just 1/2 of the reactant concentration. The dimer has 2 monomers bound together. The reaction is more like 2A goes to B. So the butadiene dimer product graph is approaching a final concentration of 0.01 molar, while the butadiene reactant concentration started at 0.02 molar. We can use these graphs and these equations to understand reaction kinetics. You will encounter these kinds of problems in general chemistry. You may be given tabular data of concentration versus time, and you have to create a graph, or you may just be given the completed graph. How can you determine the reaction order from such concentration versus time data? Furthermore, how can you extract the rate constant for the reaction from such data? Very often in science, we find that it is easiest to extract data from a graph if it is plotted as a straight line graph, a linear graph. Our math courses have taught us that the equation for a straight line is y equals mx plus b, with y being on the vertical axis and x the horizontal axis. We then call b the y-intercept because it's the value where the curve intercepts the y-axis, which corresponds to when x equals 0. We call m the slope of the curve, and it is the coefficient that is in front of the x term in the equation. Consider the zeroth order reaction. Here is the integrated rate law equation. The only variables are the A and the time. The rest are constants. We graph concentration of A versus time, which is just the data as given. The y-intercept is the concentration at time 0, A naught. The slope of the line is minus K naught. By measuring the slope of the line, delta y over delta x, we can find the ratio, the rate constant for the reaction just by changing the sign of the slope. Rate constants are always positive, just as reaction rates are always positive. So the rule you want to remember is that if you plot concentration time data as concentration versus time, and if the resulting graph is linear, then the reaction is zero order. The slope of that graph is the rate constant. Watch out for whether or not you are plotting reactant concentration or product concentration. The sign of the slope will be opposite, and you can correct that as needed. In the case of first-order reactions, we need to linearize the integrated rate law. Go back to the logarithmic form and reorganize it into an equation that looks like y equals mx plus b. Here it is. This time we plot the natural logarithm of the concentration against time. Now the ln of a sub 0 is the y-intercept, and the slope of the straight line is minus k sub 1. Remember what the original concentration versus time graph looks like. Since the original data is an exponential decay curve, taking the logarithm linearizes it, and we can more easily extract data from the straight line plot. This time the rule is that if you plot ln of a against time, and if that plot turns out to be linear, then the reaction is a first-order reaction, and the slope of the plot is the rate constant. Again, the slope will be negative if you are monitoring a reactant and positive if a product. Always change the sign if needed to make the rate constant positive. Rate constants are always positive. And finally, what if we suspect the data is coming from a second-order reaction? This form of the integrated equation is well suited to a linear relationship, except you have to plot the reciprocal of the concentration against time. Such a plot takes on a linear form. The y-intercept is the reciprocal of the initial concentration, and the slope is again k sub 2, the rate constant. Here is the original data graph. You can appreciate the nice linearity of plotting the data in this fashion. So if you plot 1 over a against time, and if that plot is linear, then your reaction is second order, and the slope is k. But here's an important warning. Because we are plotting the reciprocal of the concentration, when the concentration increases, the plot goes down, and conversely, if it is decreasing, then the plot goes up. Therefore, if you're working with reactant data, which decreases with time, then you'll have a line with a positive slope, and the slope will be the reaction rate constant. However, if you're following product concentration, then the slope will be decreasing, and the slope will be negative, and you'll have to change the sign to get the rate constant to being positive. Let's take a look at some questions you might encounter. Here are 3 different experiments. Our data is acquired by following the concentration of a reactant in each case. From this data, determine the order of each reaction and find the reaction rate constant. The approach to take is to plot a set of data against the three possible forms we have discussed. If a reaction is zeroth order, for instance, then plotting the data it produces as concentration versus time will produce a straight line plot. The same data plotted as the logarithm of concentration or as the reciprocal of concentration versus time will produce a curved plot. We could test any set of experimental data by plotting it in the three forms: concentration, logarithm of concentration, or reciprocal of concentration, all against time, and determining which one produces a straight line plot. Then we can determine the rate constant from the slope of the straight line plot. Let's first test the three data sets against the possibility that any of them arise from a zero-order reaction. We will plot all three as concentration against time and see if any of them produce a linear plot. And so, from this graph, it is pretty clear that data set 2 must arise from a reaction that exhibits zero-order reaction kinetics. Another clue could be that the set goes all the way to 0 while the others will slowly approach 0. In any case, we can now find the slope of that data set. Just use the first and last data points. Delta x is just 100 minus 0, or 100 seconds, and for delta y we have 0 minus 1 equal to minus 1 molar. The slope is delta y for delta x, minus 1 molar over 100 seconds, or minus 0.010 molar per second. Therefore, the reaction rate constant is the negative of the slope, so it is plus 0.010 molar per second. The rate constant is always a positive value, and its units will depend on the order of the reaction. When multiplied by the concentration terms, it must produce, in the end, the units of molar per second for the reaction rate. So what about the other two data sets? Are either of them first order? Well, we can plot the other two data sets as the natural logarithm of concentration against time. Strictly speaking, we shouldn't have to plot data set 2 since we've already found it to be zero order. I include it, however, so you can see how it would appear in such a plot and why you could reject it as being first order. From the three graphs shown here, we can readily conclude that dataset 3 is producing the straight line plot, and we can conclude that the kinetics behind that reaction must be following a first order theory. From that graph, we can determine its slope and therefore the reaction rate constant. Delta x is 250 minus 0, 250 seconds. Delta y, ln of 0.082 minus ln of 1 minus 2.5. Now, as a warning here, watch out that you take the logarithm of the concentration data because that is what is being plotted here. Also, logarithms do not have units, so the slope is delta y over delta x minus 2.5 divided by 250, or minus 0.010 seconds to the minus 1. Because the data arises from a reactant whose concentration decreases during the reaction, we change the sign to find that the reaction rate constant is plus 0.0 seconds to the minus 1. Now note that this rate constant has the same magnitude as for the zero order reaction. The units are different. We really can't compare the two. Finally, let's test these data sets against the possibility that there is a second order process in one of them. Again, we shouldn't have to plot data for sets 2 and 3 since we've already confirmed that they are respectively 0 and first order. I include them, however, so you can see how they appear when plotted as if they were second order data. And from this, we can see that data set 1 is linear when graphed in this fashion. The other two are clearly curved, and their data is not at all following second order kinetics. We find the slope of the straight line again to find the reaction rate constant. Delta x is again 250 seconds. Delta y, 1 over 0.286 minus 1, 3.5 minus 1, 2.5. The slope of the line is delta y over delta x, which is 2.5 divided by 250, or 0.010 molar to the minus 1 seconds to the minus 1. Now, the magnitude is again the same as for the other reactions. Yes, I designed it that way for comparison. But the units are different in each case, and you can't conclude much by comparing them with each other. They are different processes. The rate constant here is 0.010 molar to the minus 1 seconds to the minus 1. Now here's another question looking at reactions of different order. A certain reaction is found to be 50% complete after 20 minutes. How long will it take for the reaction to be 75% complete if its kinetics are 0, first, or second order? First of all, what does it mean to be 50% complete? We are assuming that the reaction, when left long enough, will reach an equilibrium point that is so dominated by reaction products that it has essentially converted all reactants into products. In reality, every reaction is an equilibrium between reactants and products, but many reactions have equilibrium constants that are so large that the endpoint is essentially complete conversion. Mathematically, this means that the concentration at this point is 1/2 the original concentration, or A is equal to 0.5 A0. From this, we can conclude that a reaction being 75% complete means that A is equal to 0.25 A0. The thing to be careful here is to not put in 3/4 or 0.75. It is what is left here that matters, not what has already reacted. In the 50% case, we put in 0.5, not because 50% is reacted, but because 50% is left to react. And it might be confusing in that case because the two numbers are the same, but remember that the equations are about what is left to react. To solve this problem, we will use the 50% information to find a rate constant, and then use that to find a time for the 75% completion condition. We will first solve this assuming it is a zeroth order reaction. Take the integrated rate law. The concentration of A at this time of t equals 20 minutes is 1/2 of the concentration at time 0, A0. We need to solve for the rate constant, K. Watch your minus signs. Half A0 minus A0 is a negative 1/2 A0. Finally, we find that the rate constant K is A0 divided by 40 minutes. Now take the same equation, but substitute 1/4 A0 for A. As well, this time t is the unknown, while we now have a value for K. It is A0 over 40 minutes. Substitute this information in, start to rearrange the equation, this time solving for t. Note how the A0s all nicely cancel each other. We readily find that t for this condition of being 3/4 complete is 30 minutes. So in 20 minutes it's half done, and in 30 minutes it will be 3/4 done, and in 40 minutes it will be all done. So this makes sense for this zero order reaction because the reaction rate is constant throughout. This will not be the case for the other reaction processes. We'll do the same analysis, but assuming it is first order. We have the same criteria for what it means to be 50% and 75% complete. Take the integrated rate law for the first order reaction. Substitute in 1/2 A0 for A when t equals 20 minutes. You have to make both substitutions at the same time for the equation to make sense. The A0s now cancel each other. To solve for the rate constant, take the natural logarithm of both sides. Remember that ln of 1/2 equals minus ln of 2. Then the negative signs cancel. Solving for K gives us ln 2 divided by 20 minutes. Take this value for K, and along with the 75% complete information, substitute this back in and solve for T. The A0s cancel. Take the natural logarithm of both sides. Remember that ln of 1/4 equals the negative of the logarithm of 4. Solving for T tells us that it takes 40 minutes for this reaction to reach 75% completion. It takes this first order reaction 20 minutes to be half done, but then it takes another 20 minutes to reach 75% completion. The reaction rate is slowing down as it progresses. Recall that the zero order reaction rate was constant throughout. So lastly, let's see what happens for a second order process. Again, the criteria for the concentrations are the same as in the other cases. Take the second order integrated rate law. Substitute for 1/2 A0 and the time of 20 minutes. The tricky thing with this equation is keeping all of the reciprocals straight. Watch the arithmetic closely and you will be fine. 1 over 1/2 of A0. 1 of A0 is, of course, 2 over A0. Subtract 1 over A0 from that and get 1 over A0. Solve for K, and it is 1 over A0 times 20 minutes. Take this value for K and the 1/4 A0 condition. We end up with 4 over A0 minus 1 over A0 gives 3 over A0. The A0s cancel. Solving for T gives us 3 times 20 minutes equals to 60 minutes. The second order reaction takes 60 minutes to reach 75% completion, even though it took only 20 minutes to reach 50% completion. The second order reaction rate is slowing down as the reaction progresses, but slowing even more quickly than first order. The reaction depends upon the square of the concentration, and as that concentration drops, it becomes increasingly challenging for the reaction to find two A's close together to be able to react. Note how the rate constant for zero order and second order processes depended upon the amount of material present at the beginning. Now, this is not the case for a first order process. Thus, it turns out, makes things particularly appealing for the first order processes, and this is another approach that could be taken to solve this problem, and we'll look at that in the next video.